Hi everyone, sorry that I couldn't make it into school today. I just thought I'd make a short video to run through the 3 anti-differentiation examples that are included on the slides. So I'll get straight into it. Hopefully by now you have worked out how to anti-differentiate. As I mentioned, it's pretty self-explanatory. There is a rule in the notes, but I always just get the little voice in my head to say add 1 to the power, divide by the new power. So let's run through that now. The first step in these problems is we're just going to simply anti-differentiate. So if we want to find out what the original value y was, we need to find the antiderivative of 2x minus 1 with respect to x. So this notation that we're seeing here, this is my symbol to say anti-differentiate. It's just a stylized S, and this is my notation that tells me that I'm anti-differentiating with respect to x. So what does that look like? Let's just do it part by part. So starting with the 2x, I'm going to add 1 to the power of x. So it was a 1 up here. It's now going to become a 2. And then I'm going to keep the coefficient and divide by that new power. Minus, and again, this minus 1 was x to the power of 0. So if I add 1 to the power, I'm going to have x to the power of 1, keep the coefficient, divide by the new power. Now there's a lot of extra ones in there. In practice, I wouldn't be writing all of this, but I'm just trying to show you because we haven't done too many examples yet. And then finally, we have to have the coefficient of integration, which is the plus c. And we spoke about how that plus c is relevant because in the original expression there could have been any constant on the end of the expression that disappeared when we differentiated. All right, let's tidy all of that up now. The 2's cancel out and I'm left with just x squared. The 1's cancel out and I don't need to write the little power of 1 up the top, so I'm left with a minus x plus c. Now what's different in today's example is that we're also going to use this initial condition up here to work out what the graph actually looks like. So what am I talking about? Let's go back to a axis here and think about what's actually taking place. We know that my function for y is x squared minus x, but there could have been any number on the end of that function. And the plus c always changes the y-intercept. So we've seen that in all of the graphs that we do. The plus c changes the y-intercept because the plus c is creating a translation up and down or parallel to the y-axis. Okay, so when I have my graph, I have my x squared minus x graph, but it could have been down here to start, or it could have been all the way up here at some point. What we've got to do is work out whereabouts that graph exists. Where should it be on my axes? Should it be here? Should it be here? I don't know, because plus c is going to tell me where that graph's got to go. So let's actually work with this initial condition to find out where that graph's got to go. We know when y equals 0, x equals 1. We can write that as a coordinate point 1, 0. We can think about that as where it belongs on our graph. I'm going to put it here and say that's 1, 0. So when I stick my graph onto the axis, I know it's got to look something like this. Okay, it's got to go through that point there. So my parabola is going to look something like that. What I now need to do is try and work out what is the c value. Now I did this graph before. I already know, or I can probably predict, that the c value at the moment is going to be at 0, 0. But you don't always have those graphs drawn before, so we're going to work it out algebraically. How do I do that algebraically? Well, I'm going to take this coordinate point over here, and I'm going to bring it all the way over to my equation, and I'm going to substitute that coordinate into my equation. So the first value is the x, the second value is the y. When I substitute them into my equation, I end up with 0 equals 1 squared minus 1 plus c, which gives me 1 minus 1 plus c, which gives me c equals 0. So I've actually found out the value of c. Now that I know the value of c, I don't need to put a plus c onto the end of the equation anymore. I'm going to take my equation, I'm going to rewrite it, and I'm going to say my final answer is y is equal to x squared minus x. And I'm done. That is the antiderivative of this equation when y equals 0 and x equals 1. Okay, let's have a look at a second example. All right, from the notes, our second example is dy dx equals 3 minus x squared, and we know y equals 2 when x equals 3. So we're going to start by finding out what y is, and y will be the antiderivative of 3 minus x squared dx. And as I've been banging on about in class, we need to show the correct notation to show what we're doing. So this step you probably should write if it was a short answer question. All right, so then from there, we need to take the antiderivative of 3. And as I said, this is x to the power of 0. So we add 1 to the power, keep the constant, divide by the new power. For the x squared, we add 1 to the power, keep the constant, divide by the new power, and put a plus c on the end. Let's rewrite that without all of the ones. It's just 3x minus x cubed divided by 3 plus c. Okay, so this is an x cubed graph. I don't know where it's going to move up or down or how far up or down. I've been given an initial condition. So I'm going to use that initial condition, which I know has the coordinates 3, 2. I'm going to substitute that initial condition into my equation so that I can find out the value of c. And that looks like this. 2 equals 3 times 3 minus 3 cubed on 3. Put my brackets in there. Plus c. Equals 9 minus 27 divided by 3 plus c equals 2. So then I get c equals 2, because 27 divided by 3 is just 9. They cancel each other out. C equals 2. Therefore, my final antiderivative, no longer with a c but an actual value, will be 3x minus x cubed divided by 3 plus 2. Just for the record, some people still get a little frustrated or confused by this. This is absolutely no different to writing 3x minus 1/3 x cubed plus 2. So that divided by 3 and 1/3, same thing. All right, hopefully that's starting to make a little bit of sense, but let's do one more final example. Example 3 from today's lesson was 2x to the power of 4 plus x, and y equals 0 when x equals 0. Should put my notation in here. We had dy dx equals that. So in order to find out what y is, we have to do the antiderivative of 2x to the power of 4 plus x, and we're differentiating with respect to x. And we know the initial condition, when x is 0, y is 0. Okay, I'll write that. Okay, keep going from here. So add 1 to the power, we get a 5, keep the constant, divide by the new power, plus add 1 to the power, keep the x, add 1 to the power, it's 2. Coefficient was 1, and divide by the new power will be divided by 2, and we get a plus c. So here's my y value. I want to now substitute x and y into this equation to find out what c is. This one's a nice and easy one, so I get 0 equals 2 times 0 to the power of 5 divided by 5 plus 1 times 0 squared divided by 2 plus c, which we get 0 plus 0 plus c equals 0, c equals 0. So my final answer in this case is y equals 2x to the power of 5 divided by 2 plus x squared divided by, oops, I messed that one up. That should have been a 5. 2x to the power of 5 divided by 5 plus x squared divided by 2. And that's my final answer. Alternatively, just be prepared. You might see in a multiple choice question, it might look like this, and it's exactly the same thing. All right, that's it. Thank you. Good luck today.